All right, thank you guys for being here again for another seminar series, another seminar in the series. What's the matter, Katie?
He's asked for another student.
Oh, I think I know who too.
Could be in his office.
Maybe not. As we've been trying to do, we've been trying to mix it up and get people from astronomy and physics and engineering. We've also been trying to mix it up in terms of recent alumni and alumni who've been out for a while, but we were having trouble hitting the middle zone. So I'd like to welcome Michael Sander, class of 2003. You know, I always have to say something, and I checked with him before. Back in 2003, when you took E&M, it was at 8 in the morning. So I want you to picture sitting in Fox's class at 8 in the morning. Okay? Maybe you did it. They've done it. Yeah. And every Friday they got donuts. Yeah, and so anyway, so if you guys did get donuts, you have a beef. Mike went from here to Binghamton, where he did mechanical engineering, and then wound up in GE's battery division, I think. And you were, and then I have to ask you something I meant to ask before, and then I will shut up. Did you cross paths with Ashley Rinko in GE's battery division?
I don't believe so.
Okay.
No. If you knew which part she worked in,
okay,
help. But yeah, she may have been after my time at battery.
It could be
as well.
It could be.
It did continue to kind of float along for a while after I left. But.
And now he's gone on to work in a topical area, especially in age of climate change and concern. And so anyway, welcome back, Mike.
Yeah, thank you.
And a little token of appreciation. So nice. And thanks for coming.
Yeah, absolutely. First, thank you guys for having me. This is a really cool experience for me. It's kind of surreal to be at the front of a room at Oneana. But so the premise of the speech was kind of given to me as I'm going to do a little bit of a career overview, a little bit about myself, talk about my background, talk about how I got where I am today. One of the things that was mentioned was that not all career paths are straight, right? It can be a little bit messy, and they certainly were for me. And we'll go through that a little bit. But so this is my background, like you said. I came here in 2002 with the intention of starting the 3-2 program, which was still very much so in its infancy back then. I chose Oneana because it's close to home for me. I'm originally from Delhi, which is just over the mountain. I actually was there earlier today. My parents are still there. And when I was leaving high school, I was really uncertain about what I wanted to do for a career. I had been doing construction from the time I was 14 all the way up until I went to college during the summers. And for a 14-year-old, I was killing it money-wise. And I was like, this is what I'm going to do. I'm going to build houses. It's going to be great. My parents were like, great idea. You're going to try college. So I went here originally with the intention of being close to home. Something happens, I'm not that far away, right? I don't have to load up the truck again and travel some far distance. But what I found when I got here was this department especially was much smaller. It was very close knit. And I found a home. I found a comfort zone. The class sizes were much smaller, and it was really nice. And I made it through that first year after they made me pick a major that first day. And I was like, you know what? Let's do another. Well, let's do another. Let's do another. And the next thing I knew, I was moving on to Binghamton. And that's where I got my mechanical engineering degree. SUNY Oneonta was a really, really great experience for me. I was elated when you reached out for me to come and talk. Every time someone asked me about coming to Oneonta, I strongly recommend it. The classes were fantastic. I still have a lot of really great memories about being in this building. And it was really weird stepping in here and having it all be different, but it's really wonderful that it grew, right? Because it was a little dark and dingy when I was here, and it was like, oh, the physics is over in the corner, right? So this is really cool. You guys have got a great facility now. So I graduated from Binghamton. Binghamton was a vastly different experience for me. It's a much larger program. There's a lot of students there. A lot of the faculty is there to do research, so it has a much different feeling in the relationship between students and faculty. The program was tough, but the curriculum was great. So we got through it, and then I started to look for a job. I graduated from there in 2008. You guys might not be old enough to really remember what the climate was like in 2008, but it was rough. It was really brutal. Trying to find a job straight out of college was tough. So my then girlfriend, now wife, she came from the capital region. So we decided to go up there because there's not a lot of engineering opportunities in Delhi, New York. And I ended up reaching out to this company, Alice Kopko, and they gave me a shot. They didn't have a lot of openings, so I ended up in a designer one position. And that is very like low level CAD. And it was really tough because I had spent all this time going to school, them telling me, you know, you're going to land a great engineering job, you're going to get a high paying salary and this and that. And I landed there. And I thought to myself, you know, if this is what engineering looks like, this might not be what I thought it was going to be. And that was the first real curve that I got in my career progression. But my wife settled me down, told me, refocus, think about what you want out of this, and let's move. So I did exactly that. I quickly moved up to designer 2, and then very shortly after that, I was a project engineer. And what I found out at that point was that I had landed myself a job, and it wasn't the career I was looking for. I wasn't inspired when I went to work. It was good work, it was meaningful, but it didn't mean a lot to me. And at the time, GE had just started to hire for this new technology that they were working on, which is the battery division. Now, this was based off from a technology that had been around since the 70s, but for GE, for the majority of the world, it was new technology. And we'll get into that a little bit later. But I landed there. The entire team was like 50 people for the whole company. So it was truly ground level. And it was a really, really intense experience and a lot of fun. So I ended up spending about 3 years there. And I ended up being the lead battery structural engineer while I was there. And then battery kind of took a nosedive. We can get into that a little bit later too. But I was quickly pulled over to wind, which is where I am now. I've been at wind for 7 years, 5 of which are my current position. And this is where I really found my footing and where my passions lie and where I want to make an impact in the world. Renewable energies is a really big deal to me. It's the path forward as far as I'm concerned. There's a lot of work left to do, but at this point with GE in this division, it's still young and burgeoning, and we can make a massive impact right now. So that's why I'm there. That's what I'm doing. So that's my basic career background. Like I said, we'll get into that a little bit more as we progress. But next slide, please. So I have 2 little kids. I have Anna, who is 7, and William, who is 5. And I was talking to them about why I wasn't going to be home today. This was a couple of days ago, and I was still kind of putting together in my brain what I was going to talk about and how I was going to talk about it. And I was telling my wife what my thoughts were, and I was telling her about like all the inputs and the output to your career path. My daughter said, that sounds like spaghetti looks, Dad. Which to me at the time, I was like, I don't really understand what that means. And she explained it to me. She's like, well, it sounds like there's a lot of starts and stops, but it's all messy in the middle. And I was like, that's like amazing. So hence the spaghetti picture. So obviously, like you guys are at a pivotal point in your life, but there's a lot of work that went into that before you got here too, right? We now understand STEM is really important at younger ages to get children engaged and get them interested in the science fields. That was something that I got very early on, but it's not in the way that it feels like it is today. I grew up in a blue collar family. My grandfather, he was a mechanic for 30 years. My dad was a carpenter. So I had my hands on that stuff from a very young age. And it was very influential in how I grew up, how I viewed the world, how I solved problems. So very early on, I knew that I was going to be in some sort of technical field. But it wasn't until older that I kind of came to the realization that I could materialize this into an engineering career. Mentors and advisors, those for me were like my technology teachers in high school, and my dad and my grandfather and anybody else. And passions, I believe strongly in keeping your passions alive outside of work. Mine are not related to renewable energy, but they're all very technical. I still work on cars. I do a lot of construction. I brew beer, and all these things are sciencey in their own way. And they all help me be a better problem solver, right? Life experiences and exposures, skill sets, that's a huge one for me that I'll get into. Education, of course, pre-career work experience. Education and pre-career work experience, I can't underscore those enough. Education is super important. Pre-career work experience is massive. And I took it for granted. I did not do any internships. I didn't do anything related to engineering before I entered the work field. And that affected my early career progression greatly. So something for you guys, pursue those opportunities. Get work experience early. You'll spend a lot less time wandering around once you do get a job trying to figure out what you're passionate about, and more so what you're not passionate about, because you can spend a lot of time doing something that you realize, this isn't for me, this isn't what I thought it was going to be. So grab those opportunities when you can. Skill sets is a massive one for me. That's gotten me where I am today. I work mostly alongside engineers with master's degrees or PhDs, and they went to MIT or these other massive engineering schools. And I went to state schools. And for a lot of companies like GE, they look immediately towards these really high-end private schools like MIT and RPI and RIT to grab those people. So you have to have something that helps you to stand out. Skill sets for me was that thing. When I went to battery, can you actually skip 2 slides ahead? And I'll just talk about that real quick. When I went to battery, I pulled every string I could. Every person I knew who worked at GE, I reached out to, and I asked them to help get my name in somebody's ear. And when I got there, my interview lasted for 8 hours. And my first interview was with my future people leader. And he, without speaking to me, walked into the room I was sitting in, like a little room, with a box full of parts. And he said, I saw on your resume that you know how to weld and you have weld experience. And that's why you're sitting here. And he took the box of parts and he dumped them out and he roughly separated them. And he goes, I need you to classify these by type, good or bad, and why they're bad. And then he walked out of the room. And that was my first exposure to GE. And I was like, is this what they do for everybody? Because this is madness. Like, this is lunacy. And so I sat down and I worked all the way through them. And I came back in and he just looked at the table and he kind of smiled and he was like, all right, okay, let's do this. And then I went on to the next one and the next one and the next one. And the only reason I made it to that next phase was because of skill sets that I built when I was like 12 years old when I first started welding. That's the only reason I stood out against the other candidates. So I cannot emphasize that enough. Work on those skill sets. Things that you think may not apply now may have a massive impact on your career in the future. That being said, I have those skill sets because they're my passion. And at first, when I entered this career field, I didn't think that my passions could drive my career progression, my personal passions could drive my career progression. But in reality, the more I focused on them, the better fitting positions I found and the bigger impact I could make. Let's back up just one slide. So Atlas Copco. I went over this a little bit, but I just want to talk about what the equipment was. So they do really big motor-driven gas compressors or gas and process type compressors. So my job was, at the time in 2008, we were still using 2D CAD to model these pieces of equipment. And then we had to go through our design reviews and try to walk people through these two-dimensional models and insist and imply and show that these are going to work for our customers. And then they'd show up on the factory floor. We'd spend months on the floor trying to help build these things because we drew them with just click, drag, click lines and nothing fit, right? It was a really great experience, but I immediately knew it wasn't for me. So then I moved to battery, and we'll go to the next slide. We'll talk a little bit about that technology. So, like I was saying before, it's a startup environment. We really didn't even understand the market that we were getting into. When I first came on board, they had 3 big picture ideas, but we really didn't understand which one we were even going to go after yet. And we still had to make the technology work. And as a result of how I did in my interview, that job was very hands-on for me, which was perfect because I love being a hands-on engineer. I hate being chained to a desk. I set up a lab there. I was on the factory floor probably 6 hours a day working out manufacturing issues, coming up with different design solutions. And this technology is really what helped to show me the kind of impact I could have on the world. We were talking about putting these in the most remote areas of the world. We're talking about African desert situations where in the telecom industry, all of these towers are powered by diesel generators, and people are driving out there every day, sometimes multiple times a day, to refuel these generators. And because of the economic climate out there, those generators were very frequently vandalized, the fuel was stolen. It was impossible to keep the grid up and running in these areas. These batteries, as a function of their design, also made them incredibly hard to steal. This battery, which is a telecom battery, that weighed about 680 pounds. So you can imagine, you show up at one of these towers looking for diesel and you see this nice new shiny battery. Well, what does that do? Can I take that? Can I use that? Because they were using a lot of lead acid technology to support brownouts or diesel generator dies, and they got to keep it up and running. But they couldn't. And we spent a lot of time designing in anti-theft features. You can see these little buttons on the side. That's how you lift the battery. And we intentionally designed them that way because you can't grab a hold of them without the tools and lift that kind of weight. So these were when you're in a startup, these are the type of design challenges that you're frequently facing because it's so new to the market. You end up working on stuff that you didn't even understand to be a problem when you came up with the technology. The other big technological challenge with these batteries was the temperature that they need to operate. So these are sodium nickel chloride batteries. Nickel, being a metal, is in a solid state at room temperature, right? So that means to get these to work, they cannot be in a solid state. These batteries operate at 750 F. So these batteries also have to be safe for people to be around and for people to touch, which means that between the cells, which are shown here, and the outer skin, we had to drop, call it 650 F. And there's also packaging constraints, right? Because these things can't be massive. You can't have a foot of insulation around them. So what we ended up coming up with is we have an inner box where we put all of these cells in, and then we have an outer box, and between them, we used a foam silica type insulation, and we would pull a vacuum on the battery. This ended up being, at this point in my life, the biggest technical challenge I have run into. We have to pull these batteries down to a near perfect vacuum, as close as we could realistically get in a manufacturing setting. And then we had to permanently seal them, because if we were to put a vacuum type system on this equipment out in the field, it would put us well beyond the financial range of being competitive. So we leveraged another industry, which is something that you guys will probably frequently run into in your career. It doesn't, like when you're working on new technology, it doesn't always mean that you have to come up with new technology. There's lots of opportunities elsewhere in the world where somebody else has already solved your problem or close to it. So all of you have this technology, that vacuum technology in your house. It's in your refrigerator. It's in your AC systems. They draw a vacuum on that. When they build that fridge, they use hydraulic welding crimpers to crimp the copper tube that they're pulling a vacuum on. So we leveraged that. Our tools obviously got significantly bigger. The materials themselves were significantly more challenging to deal with because of the life term that we were trying to get to. These batteries were supposed to last 20 years. We were supposed to hold a 20-year vacuum on a welded assembly. That's darn near an impossible task. And to be totally honest with you, that was probably one of my biggest first career failures in that industry. This was a task. It was impossible. We knew it was impossible. We addressed it like it wasn't, and we marched forward because that's what you do. But at the end of the day, these vacuum systems were unreliable. We're talking about crimping a tube that's maybe 1.25 inches, and you have to have a cold weld seal. You're smushing metal together so hard that you're depending on it to hold a vacuum for 20 years. In addition to that, all these dark lines on the perimeter are welded seams. So all those welds have to be vacuum perfect. It was incredibly challenging. I learned a tremendous amount doing it. If you guys ever have the opportunity to get in a startup environment, do it. You'll learn more during those couple of years than you will in 10 years in a well-established product line. You'll learn how to deal with difficult personalities and flared tempers. There's a lot of that in startups. But it can be a lot of fun. And I'd say do it while you're young. Don't wait till you're older to try it out because it's very time intensive. I did put a video on there. If you can click that, it explains the technology a little bit more. This was, I think you guys hit just control and then click it.
I have to share. This is where Zoom complicates things.
So you guys will see in this video too, another spot where my hands-on background and my personal hobbies came into play as well. The actual prototype battery that is in this video, it's green. They had this special RAL color for that technology. And I was brought in early on because I was a car enthusiast and I had let somebody know that I had a powder coating set up in my garage at home with like a kitchen oven. And they tasked me with bringing this home. So I built the box and then I brought it home and I powder coated it in my home garage. So, and these are all things that like when you're starting, you're like, oh, you know, this is kind of a sidebar, but in reality, I made so many connections through just that one part of my job that it kicked a lot of doors wide open for me. it gonna play? Yeah.
Should.
Okay.
The Durathon battery is based on sodium metal halide chemistry, first developed in the 1970s and later refined by GE Global Research. This metal salt technology is the heart of the revolutionary Durathon battery. The core of the technology is based on a ceramic beta aluminum tube, which is impermeable to liquids and gases. This ceramic tube holds the cathode materials comprised of sodium chloride salt, nickel, iron, and a salt-based liquid electrolyte. The reservoir surrounding the ceramic tube contains the anode, which holds the sodium metal upon recharge and features proprietary construction and additives. Each cell features a metallized ceramic top piece, which completes the electrical connections. Once the cell reaches its operating temperature, the ceramic tube becomes an ionic conductor, capable of transferring sodium ions between the cathode and anode. When a charging voltage is applied to the cell terminals, the salt is converted into nickel chloride, and the sodium is transferred to the anode reservoir. When the cell discharges, the chloride is released from the nickel, and sodium is drawn back into the cathode, returning to form salt. Each cell has an open circuit voltage of approximately 2.6 volts and has a capacity of approximately 40 amp hours. Comprised of many cells, the Durathon battery module pictured contains over 200 cells strung together in series, resulting in an energy-dense 550-volt battery. To minimize heat loss from inside the battery enclosure, a super-insulated outer box is used. This highly efficient double-walled insulation system enables the outer skin temperature of the battery to be only a few degrees above the ambient air temperature. This battery features electrical heaters to help regulate the internal temperature of the battery. For demanding applications, a forced air cooling system removes excess heat from inside the battery. The Durathon battery is not just robust, it's also smart. With an integrated battery management system, these batteries are capable of remote diagnostics and real-time monitoring. When not in use, the battery will cool, freezing the chemistry in a dormant state and maintain its charge. In this state, the battery will have no reduction in capacity or self-discharge and will have an indefinite shelf life. Durathon batteries can be assembled into modular racks that are capable of being aggregated into full systems built to various performance specifications, well suited for a variety of industrial applications. Durathon batteries can be used in fields such as utility transmission, renewable power generation, telecom power support, uninterruptible power supply, and industrial motive transportation. GE manufactures this battery system in its state-of-the-art facility in Schenectady, New York.
Okay, so that one didn't have the actual. So this was very early on. And what we found out later on was we really couldn't be cost competitive in a lot of those industries. So we pushed to different industries. And the one where we were working the most on towards the end was the mining industry. Okay, so the mining industry, they very typically on their battery powered units, they're using lead acid batteries still, sometimes lithium ion, but there's major downfalls with both of those battery technologies in that there's off gassing in the lead acid batteries, and lithium ion, of course, have these potential catastrophic issues with thermal runaway, and you can cause fires like we saw on airplanes for a period of time, right? So we jumped in there, we did a lot of research, and then I got really, really heavy into halt type testing, which is highly accelerated life testing, where we essentially shake the crap out of these things for like days on end, and then pull them apart and figure out what failed. You guys can imagine when you're dealing with ceramic tubes inside of cells and vacuums, that sort of environment is not very conducive to the life of that equipment. So we ended up having a lot of things with this technology that stacked up against us. One of them was just was just ramping production up to a level where we could get our cost down per unit because the chemistry can be so finicky. We were talking about hundreds of grams between a bad cell and a good cell when you're pouring in the melt chemistry. And that's really, really difficult to address in a manufacturing environment. The other, of course, was the vacuum issue. And then finally was the cost issue. We just could not get the cost of storage down to a level where it was really, really attractive to these industries. And at that point, GE made the decision, okay, we're not going to progress forward with this. We're going to go back to our typical model, which is to source equipment from the industry and be the provider of solutions. And so anything related to energy storage now, to batteries now at GE, are solution systems. And this was very outside of GE's wheelhouse to get into being an OEM. And I think it'll probably be a long time again until they get back into it because it didn't really go that well. They ended up investing about $200 million. And then at the end of it, they just kind of trashed it all, moved on, got their losses. So at that point in time, I had made my name for myself at Battery, being a very hands-on person, the way I address problems, the way I chase down problems and think about them. And somebody at Wind had heard about me and a couple other guys that I worked with, a couple other folks I worked with, and they pulled us over immediately before we could leave the company. You can go to the next slide. And that's how I ended up joining Wind. Wind at that point in time wasn't something I really thought a lot about. And then my first week I got to climb, which was amazing, and I was hooked. Wind turbines are, I mean, when you look at them from afar, they don't look that massive. They are huge. And when you get on top of them, like these pictures on these units are 100-meter towers. So you're 300 feet in the air. And that is, you know, even to just be up there can be frightening, let alone work up there, which is what I ended up getting into. I spent my first 2 years at Wind as a fleet performance engineer. And what that essentially boils down to is we have all these wind parks throughout the world, and frequently wind turbines are down. And GE supports those sites by having engineers on hand at all times to help troubleshoot those. It was a really great way for me to get my foot in the door. I learned a lot about the technology, but for me, not being able to sit at a desk was really challenging. And my manager, who was fantastic, I'm still very close with him today, he saw that, and he had an opportunity for me to go up to Niskayuna, New York, which is where I'm at now, and they had just started a repair development facility. He loaned me out, and I just never went back. Like, yeah, I went up there one day, and I went back down to main campus, cleaned out my desk, and I just never went back. So that's where I am now. What's the next slide look like? Okay, so I'll get into what I do now, but the next slide is a video. It's one of our newest wind turbines. It's a really cool installation video that I had a part in creating. It'll kind of give you an idea of some of the work that we do.
Reduce your electric bill with the Generac power cell. Click here and learn more.
So these units are primarily in Europe. I'll talk about the different types of wind divisions. But these units for an onshore unit are absolutely massive. You'll get, in some of the images, you'll see people in the equipment, and you can get an idea of just how big they are. So there you can see landing the towers. So these yellow twisty things are vortex shedders. So what we do is we temporarily install them on the towers to shed wind. Otherwise, we get massive oscillations in the tower. If you're actually designed in a way where if you don't have to wait on top of the towers and then begin to oscillate like that, they'll actually come. This assembly is about 70 tons. So, like like this lifting beam, this whole process, both this lifting beam is part of what the team that I'm on develops, works on. So we do installation and repairs. You see the little cranes down here. The cranes that we use, we can talk a little bit about them. We actually, for something like this size, we bring 3 to 4 cranes on site. Each crane builds the next progressively larger crane. So we get to a crane size where we can actually reach. Okay, next slide. So we'll just kind of walk through fundamentals and the stuff that we focus on. So obviously, some of the more obvious stuff is the tower. This is called the nacelle. So the nacelle is actually the enclosure that all of the equipment lives in. This is the hub, the blades, of course, and they're fundamentally very simple machines until you actually get down in the nitty-gritty of how they operate. And then they become very finicky and very complex. But essentially, you have your hub that's spinning. It's around 17 to 25 RPM, depending on the equipment type and the size of it. And we can operate at any speed after a certain point. So I think it's like 10 meters per second you can actually operate. And we do that because, and I'm not going to get into too much detail because I'm going to get in trouble because you guys are smarter than me on this stuff. But what we can do in the generators, we can mimic fields so that we can run at different speeds, but still output 60 hertz to the grid. Because otherwise we have to run at 3,600 RPM exactly, right? And that's not possible. You'd be running 10% of the time, right? So once they figured that out, they made it so that we could start to scale up in the wind industry and start making significantly more power than like the little wind turbines you might see on like a farm. Not windmills, but mini wind turbines were very popular for a while, and they put out, you know, maybe a couple hundred watts. That unit that we just watched the video on puts out about 4 megawatt. So that unit, one full revolution at optimal speed will power a house for 2 days. And there's usually, depending on the wind farm, I mean, you can have anywhere up to a couple hundred of those. So power in, pretty basic gearbox, multiple planetary stages and a helical stage usually, an output at 3,600 RPMs to your generator. You have all the controls, and then you have all the smaller equipment. So something that I was completely unaware of when I joined wind is that, and it seems obvious to me now, but not only do these things, the candlestick on top of the tower to turn in and out of the wind, you almost always have a prevailing wind direction, but it's never straight on in the most efficient direction. So you have to turn into the wind. And then in addition to that, the blades turn, they candlestick on their axis. You guys will find, if you go look on YouTube, you can pretty quickly and easily find videos of wind turbines that have caught on fire. It's very dramatic. That's what faced the public a lot early on. That's not typical. Something catastrophic happened there, and it's because the blades stopped turning. The blades are actually the primary braking mechanism for a wind turbine. So you're not actively braking, you're turning out of the wind so that it stops pushing your rotor. Secondary to that, in the event that you, for any reason, lose control of the ability to pitch, you have a secondary brake, which is just like a disc brake on your car. And it's on the backside of the gearbox, so it has the greatest mechanical advantage to try to slow things down. That's when you see those turbine units catch on fire. It can slow it down and turns out fiberglass is pretty flammable, so you end up in that situation. But we've gotten to a place in the industry, and different manufacturers do it in different ways, but we have redundant systems to make sure that that doesn't happen. All of our pitch systems are battery backup. Some of them are hydraulically controlled, so you don't rely on electricity at all. And again, something that didn't seem really obvious to me when I joined. The wind's not blowing. You're not making any power. You're not charging the batteries in the hub to turn these things off when they need to when it starts running. So we actually use what are called defib generators, which are doubly fed inductive something generators. And that means that we can send power in both directions through them. So even when there's no wind, we're sending power up into the unit so that it's online and ready to make power as soon as the wind starts blowing. Next slide. This is just a little bit more detailed version of that. This is actually a GE, like it's a dummy model that we might give to a vendor so they can size equipment based off from our model. So you got your hub, right? And you've got big bearings that control the blades, and then your main bearing, gearbox. These are your yaw drives. So that is what allows you to candlestick on top of the tower. And then back out through the generator, you have what's called a flex coupling here. The majority, for GE at least, of failures that we see are related to bearings and gearboxes. Especially, we had a fleet-wide issue with our pitch bearings, where they kept eating the ball bearings and spitting them out and nearly losing blades out of the hub. And it turned out that we weren't the only ones suffering from that issue. And it's a fundamental issue with what we're asking a bearing to do. Bearings are not designed to take loads in the directions that we're putting loads into it. So bearings want to spin about an axis, right? And we're asking them to take massive loads like this and continue to spin. And it turns out we're never going to win that battle any other way but with size. So we continue to make these bearings bigger and bigger and bigger. And we never expect them to last forever. We just ask them to last the 20 years that we want the turbine to operate in. Main bearings are another one. We're asking that bearing to do the right thing. The problem is that the loads that we put on it are just astronomical. And if the metallurgy is not perfect, turn those rollers into powder in a hurry, or we'll get small pitting on it occasionally that is from voltage transfer. If we have stray voltage, especially in the event of like a lightning strike or something like that, it'll actually pass through that bearing and it'll create little dents and stuff in the bearing, and then that gives it an opportunity to start chewing those ball bearings up. And then finally, the gearbox. Gearboxes are big, they're heavy, they're not especially different than gearboxes you would find in a comparable industry where they need one. The problem is that it's a big financial driver for wind turbines. So we usually end up going with the most cost-effective solution, which frequently ends up with quality issues. And when you're talking about, like we have installed base, I think of like almost 50,000 wind turbines in the US now. We run into issues in the hundreds frequently, not like across the entire fleet, but we have gearboxes that just come apart, or they have failed bearings, or they have, again, metallurgical issues with the gear sets. All right, next slide. So this is a really good example of the type of work that we chase after in the division that I work in. So the slide's kind of what I do and what the team does. I'm the operations leader and senior engineer for the team in Niskayuna, which means that I essentially run the day-to-day operations in the facility itself, where we do all the work and the engineering. It also ended up being kind of a mentorship role. We have a lot of really young engineers. This industry is a big draw for young engineers. So I end up in a situation a lot where I'm mentoring these younger engineers and helping to teach them how to solve problems the right way. We're really, really big on design thinking and now lean. GE is bringing lean back, which is both of those systems are just technical ways to lay out how engineers naturally think and help to guide them. So anytime you get in a situation with lean or design thinking, all it is iterative improvement, right? So like what we preach at our facility is speed, because our industry demands it, requires us to prototype quickly. And we get through problem solving by defining the problem and immediately going to prototype it. So my shop that I built out, it's got a full machine shop, it's got a full weld shop, it has a wood shop where we have a CNC router and we have all this tremendous equipment. And what it allows us to do frequently is cut months, sometimes even years off the design cycle, because we can just go in there, knock out a prototype and go immediately out to the equipment that's in the lab to try it out. When I started, so year one, we had 5 people. We were a homeless team. We didn't have a shop set up. And we had one project that made a massive impact. And we were just kind of a ragtag group of skunkworks type engineers who couldn't sit at a desk. So we were perfect for it. Ann McAtee, who was the CEO of renewables at the time, came to us with a problem that she said everybody in the business said was impossible. And she wanted us to figure it out in 6 weeks. And that was a main bearing failure on a piece of equipment that it was designed so that the main bearing was not a serviced part of the machine. Originally, what they had done is they had split our bed plate in half so that you could pull the bearing out. And then they decided, because of cost outs, which you'll inevitably run into in your career, that they didn't want to do that machining process. So they just press fit a bearing into this massive piece of steel, hoping it would last a lifetime. Well, it didn't. We immediately had failures. The first failure cost the company, I think, 8 months and $4 million to repair. This is on a machine that only cost $1.2 million to build. But that was our commitment to the customer. So we were asked to come up with a more cost-effective solution. We came up with a series of processes and tools that allowed us to push that bearing out at site, because the original process required us to fully disassemble the wind turbine, ship it across the country to our manufacturing facility, repair it, ship it back, reconstruct it. So all the crane costs and everything come into play there. So the ask was reduce as much as you can, time and money wise. The last one we did, we cut 8 months down to 17 hours and $4 million down to $220,000. And we had something like 1,200 units to repair. That year alone bought us like the next 10 years of salaries and equipment that we need. So immediately we had a name for ourselves. And it's all because we were all similar engineers. Like we all came from hands-on backgrounds, but different. And we embraced that early. We had guys who were machinists, guys who were welders. We had guys who were just great at prototyping, great through thinking through processes. And we just, every day, collaboration in a design thinking space to figure out next steps, just eating the elephant. Now, year 5, we're at 70 plus people in our group, growing. We have a 20,000 square foot facility. And I'm in the process this spring of bringing a Germany facility online that'll be comparable to this. So the business is now seeing, you guys have made enough impact in the US that we're going to do another one in Europe. And then we'll do one in Manat, and then we'll do one in Latin America. So within the next 3 years, we'll have one of these teams in each one of those locations. So obviously, challenging start, right? But now we're at a place where we've grown to be a massive part of the business. Services, it turns out, will be most of the direction for financial gain in the wind industry moving forward. It's going to be a lot like the car world, where dealerships are not making a tremendous amount of money on the sale of a car. They're making all the money when they do the repairs on it, right? So the work that we do, It's called Up Tower MCE, and then we work on catastrophic failures, installation, and tooling engineering. So like what you're seeing here, once upon a time, gearboxes were not supposed to be removed. You just swapped out full machine heads. So you take down the rotor, you take down the machine head, swap it out. And then we started figuring out, well, we can actually pull these off Up Tower and send them down and just swap a new one. Now we're at a point where we're modularly disassembling these gearboxes in the machine head, Up Tower, and replacing parts and pieces. So that's what the industry has started to demand. That'll be the demand moving forward. What's driving that is we don't want crane costs. Like I was pointing out before, you have to send between 2 and 4 cranes to any site where you have a catastrophic failure like this to get a crane big enough to lift that load. So in an easy to access place in Texas, $150K just for the first day. And then it's like $20,000 after that each day. Difficult areas, if you've ever driven through like parts of Pennsylvania, you'll see wind turbines on ridges. It's next to impossible to get cranes up there after they're erected. You're talking $400,000 to get a crane out there for a repair. That's on a project where the gearbox costs $400,000. So the ask for us was to figure out, okay, you break it down into manageable size bites. And we started figuring out how to repair sections of these gearboxes and ensure that we're getting that. So material handling is probably the biggest challenge that we face as a group. You're still lifting pieces of the gearbox. Like you're lifting the planetary stage, talking about 19,000 pounds, helical stage, 17,000 pounds. You're doing this all in a space. I mean, you have less space to move around than behind this desk at any point inside of the machine head. And we're now using what are called Up Tower cranes to do the work. So we don't bring these up with cranes, we bring these up in pieces and build them Up Tower and do the work. This one has roof sections removed, but what we typically do for repairs is we actually leave the roof on, but retract it. We built systems so that we can lift it up, put it on rollers, and roll it back and do the work. So that's the type of work that we do. It's extremely technically challenging, and every year we start working on the things that 2 years ago were impossible to even fathom us to. So it's that incremental pushing the envelope. I think just one last slide. Future wind. So for anyone who follows renewable energy at all, or energy in general, we now have a really good understanding that there is no silver bullet for the energy crisis, right? We understand now that no matter what the solution is, it can't fix everything. So it's got to be a portfolio. Similar to like how we use now in most electrical grids, we have this balance of plant where we might have a natural gas turbine that supplies the majority of the energy and it's backed up by a massive wind farm. The linchpin moving forward is energy storage. Obviously, wind isn't always blowing, sun isn't always shining. So we need to be able to capture that energy, whether it's hydro or batteries or some other method, before we can really get to the point where this is sustainable and we can move forward without carbon-based fuels. Onshore wind, we're working on some of this now. We're getting to the point where our fleets are aging. We're hitting that 20-year mark on some wind turbines, which means that it's very old technology and those parts are worn out. And we're working now on programs called repowering, where we come in, we use the same tower and we'll put a full new machine head on it. That's like double the capacity, or we'll go in and we'll change the gearbox, main shaft, the generator, and we'll be able to double the capacity of the wind turbine and cut the price more or less in half. The challenge for onshore wind right now is most of the prime real estate, great wind farms, are already taken. So we're working with less and less prime real estate every day, which brings greater challenges to the table. And with that comes size. There's size restrictions and different needs. In Texas, you put up a fleet of our smallest, least expensive wind turbines, talking thousands of wind turbines, as far as you can see. If you get on top of one, you look miles in any direction. You can have that. Other situations, like if you've ever been to Chimney Peak in New York, they have a wind turbine over there. You can get one. That's all you're getting. So you need to have different equipment for those different situations. And it's different in Europe too. We have what's called land constrained units in Europe, and they're massive because you have such a small footprint that you need to create a much larger wind turbine to make the most out of that wind. Offshore wind, you guys will hear a lot about offshore wind in the next couple of years. Albany is turning into a bit of a hub for offshore wind. There's production coming there. It's the only waterway in the Northeast that's available year-round. So they can go in and out of port year-round to construct these wind farms offshore. There's one off the shore of Block Island. There's another one going off Martha's Vineyard. They're becoming very popular in the United States because we're finally accepting that we're very vain historically about our coast areas. Nobody wants to look at wind turbines, so we kind of turned our nose up at it. But the reality is they can have such a massive impact on our coast efficiency as far as electricity and power goes that we just can't refuse it anymore. Offshore wind has been huge in Europe for years. They've had wind farms out there for 30 years now on the water. And the greatest part about offshore wind is that these units can be absolutely massive. You're not land constrained. Our unit that we just released this year is 12 megawatts. So one revolution on that will power like, I don't know, 12 homes for 2 days. So you can imagine, and the wind is constant, right? Like if you've ever been out on the ocean, it's very consistent and it's very pleasant to make power with. On land, you can get gusty areas that are really hard on equipment, or very pitchy areas where it's very fast 1 minute, and then it'll slow down and stay like that. And then out of nowhere, come up again. Offshore is just very super consistent power. That's it, guys. That's all I've got. I'm hoping you have a pile of questions for me. Yeah.
I was just wondering, like currently with how much wind power that we're using in the United States, like how much power is that really accounting for that we use?
That's a really good question. I don't have the numbers in my brain, but it's order of magnitude in certain areas. Texas has had days where they could be 100% renewable.
Yeah, I've heard places like Texas where like sometimes all the power is coming from wind. Yep. The power that you're making, does it get stored or is it pushed like directly onto the grid to be used? Directly onto the grid, which is another challenge because when you get into super remote areas, if you don't have grid accessible, but you've got a fantastic piece of land to put a wind farm, you have to spend the money to get the grid out there. Right. And then of course you have losses. I mean, you're at 32 kV, so your losses are minimized as much as possible, but it's still there, right? And then there's other parts of the country where wind just doesn't make sense, either politically, that it's a climate that it's just not something they're interested in, or there's just no wind. The Southeast, there's no wind in the Southeast, but they have a great opportunity to do offshore. And they're hopefully, offshore is a really, really weird business because it's international waters, right? So no one has ownership of it. So we as society have to say, okay, how do we do this fairly, right? Because you can't sell ocean property like that. So what they're doing is they're creating a bidding system where they're saying, hey, this area has been defined as an opportunity and we're going to allow everybody to bid on this area. And it frequently goes into local government, like the state, or just national government, right? And those costs are rising every time they do an auction. So overall, I'd say less than 15% of the country is wind power. We have a lot of hydropower. There's a lot of nuclear power in the United States, but there's certain areas that just, you can't have wind.
Yeah. Anybody else?
So I was wondering, 20-year lifetime, but you're repairing these. How long does a typical wind turbine go before you have to repair it on it?
That's a really good question. It varies dramatically across different product lines. It also varies depending on location. Some equipment that kind of got rushed through the design cycle because of demand, like we saw major failures within 2 years. And we understand that now as a massive misstep, right? That wounds our relationship with the customer, it hurts our reputation. But at the time, in the wind world, they wanted a product cycle of like 2 years. They wanted new equipment every 2 years, new product line, like cell phone level rollover, instead of like 10 or 12 years in the automotive industry where you have time to actually develop this equipment. They wanted it much faster, which pushed us to make poor design decisions. And a lot of times it was addressed as a risk factor. And we just looked at it and we said, we're willing to take this risk that this might not work. And we were borderline on our designs, and we ended up eating it, and we got a little pie in the face. But some of our units, like the early fleet, our 1.6 and 1.7s are absolutely bulletproof. Like they will frequently, there's some that really haven't needed anything aside from oil changes for 15 years. Other ones, like location dependent, the Midwest is really, really hard on wind turbines. Believe it or not, the dust in the air will erode blades at a rapid rate. And it will actually eat through the fiberglass on the blades. So you end up having to repair or replace blades. Also, Tornado Alley is pretty rough on wind turbines. Cold areas, we have a lot of wind in North and South Dakota, also up in Canada, but we have icing issues there. So all this freezing cold air coming across the blades causes droplets to freeze on the blades and condense. And then we actually, like we have de-icing programs to prevent it, but occasionally like you'll see a video of ice shedding off a blade and it gets launched like miles. You have to remember tip speed on some of these rotors, like 120 meter rotor. I mean, you're talking hundreds of miles an hour, hundreds. It's wild. Some things you might hear of in the media is related to like protected species. It's really not as bad as it sounds in the media. Condors, predatory birds are a big concern, right? It's been years since I've heard about a site with an issue. We actually have bird mitigation programming that we use in the machine heads. So they actually use LiDAR on site to see when there are larger bird populations, and they'll turn off certain sections of the wind farm to prevent blade strikes with birds. So it's not that common. We are really careful about it. Like there's certain species where if you see like certain types of desert foxes and stuff, certain types of smaller animal breeds that theoretically the sound can disorient them and make it harder for them to return to their dens and stuff, we'll turn off parts of that farm too based on sighting. So conversely, when we go out to site to fix them, especially in Texas and the Southwest, frequently run into rattlesnakes, black widows. You'll open a cabinet door and it'll be full of black widows. And it's usually like, it's not at the beginning of the day, it's at the end of the day when you're super tired and you want to just get back in the truck and go back to your hotel. All the rattlesnakes will go underneath the truck because it's nice and cool from the shade. And you have to do like a truck inspection from like 10 or 15 feet away to make sure there's no snakes underneath the trucks. And baby snakes are the worst. Baby rattlesnakes are the worst because they don't understand that they shouldn't strike with their full venom, their first strike. And they're harder to see. So we run into that occasionally. People will get bit and stuff.
Sounds like my kids.
Safety is another big part of the industry right now, of course. We're in a stage in the industry because it's growing so rapidly and we have so much unskilled labor in the field. Unskilled labor frequently translates into injuries. It's industry-wide, and we're working across manufacturers to help mitigate the problem. But the problem is that so much of this equipment is catastrophically dangerous, right? Like the weight of the equipment, the voltages that we operate at, the amperages, the heights, of course. We all carry emergency descent kits every time we go up. We're trained on it every year, in the event that you have to get off the side of the machine head or something. But safety is a big one. It's a big part of our job too. I mean, we spend weeks per design just on safety analysis.
Emergency descent parachute?
No, you rappel.
Oh, okay.
Which is maybe worse.
Right.
Yeah.
Yeah.
No, so you carry enough meterage of rope to get to the bottom. So you have to be very cognitive of what you're bringing with you, because we have 80-meter towers and 100-meter towers in the US. You obviously don't want to be in a 100-meter tower with an 80-meter rope. It's going to end badly for you. So, some of the other really cool repairs that we do in the industry that I'm not part of, blade repairs, they use what are called rope screws. And just like window washers on skyscrapers, these nut jobs scale down these blades and are doing fiberglass repair with them installed. So they're there with a grinder and epoxy and fiberglass repairing these blades. Yeah. Yeah.
So solar power.
Mm-hmm.
Solar cells, we don't have all the moving parts, and obviously those kind of concerns are much smaller. Like, can you say a few things about like what's the difference? Like, if you wanted to make a solar farm using state-of-the-art solar panels, how big would the farm have to be to compete with one of these blades? And is there some kind of competition in the industry between solar and wind?
I wouldn't call it competition. I would say that most places where they've got adequate sun and wind, they just take a look at it from a pure financial sense. You have to remember that a lot of wind farms are leased from farmers, right? Under the premise that it's not going to interrupt their profitability. So wind farms are a little bit different. It's harder to graze animals around massive wind farms. It affects crops differently. Like if you're in a cornfield and you have the base of a wind turbine, which is maybe, let's call it 30 foot in diameter, outside of that, nothing's really affected. But if you have an entire solar farm, even if, and I understand that there's certain scenarios where you can still maintain really good growth, it's a lot harder to farm certain crops around that. So I think it becomes more of a logistics issue and financial gain issue. I think in the right situations, so maybe more arid situations where you have a tremendous amount of sun, you're not really farming the land, solar might be a better option.
How big would the area of a solar farm need to be to compete with one turbine?
That's a good question. I'm not really sure. It would have to be pretty large, right? I'm not sure, like I'm not in solar, but we're talking about how many watts of power does like a middle of the road solar panel put out? I don't really know. Let's call it 50, right? 50 watts of power, 400. Okay, so 400, whatever it's, we're putting out on our smallest machine, 1.5 megawatts. So you could do the calculation relatively easy, but so yeah, I think it's probably up for consideration, much like hydro is. Anywhere you have is like a place where you have potential for hydropower and wind at the same time. If you can't come up with some combined wind farm, hydro farm, you're just going to look at it financially. It used to be with tax credits, wind was a lot more affordable. Certain administrations are a lot more friendly to wind than others for pretty obvious reasons. And the last administration pretty well killed all tax benefits. So what we did was because the tax benefits went away, we repowered units. Like we switched almost all of our business over to repowers. And that was because the cost is so much lower for the end user or the owner that they could swallow that cost much easier. You're talking, you know, if you do a drivetrain swap, maybe a couple $100,000 versus a whole new machine head at like 1.5 million. Yeah, I saw another question.
I want to bring us back to the size of these for a second. So obviously they're large and tall because the higher you go, the faster the wind speeds, the more power you can generate.
Yeah.
Have we found the sweet spot in the way that we design them now, where we can't build them any bigger, maybe because it's not practical, and smaller ones we wouldn't generate enough power, or is there still a lot of room for redesign and maybe more efficient ones in the future?
Yeah, that's a great question. There's a lot to unpack there. I'll address it based on wind speed first. Much like in any fluids dynamics type scenario, the closer you are to any surface, the more disrupted the airflow is, right? Like you want to get up into that laminar consistent flow. So there is a minimum height. The maximum height is dictated more on infrastructure. You're going to see more and more in the media discussions about like 3D printing tower sections on site. Global Research Center for GE, they have out towards Rochester, they have a concrete printing machine now that's working on printing tower bases. And that's because tower bases, as we go taller, bases have to get bigger in diameter, right? Almost anywhere you go in the United States, you're going under an overpass at some point in time. We can't feasibly weld these in the United States on site. We just don't have the quality control. So that means that we need to figure out another way to build them on site before we go up. But what we'll do is you won't ever, I hesitate to say ever, I shouldn't say ever. More than likely, you won't see the entire tower fabricated on site. What you're going to see is these biggest sections fabricated on site, steel tower sections on top of that. Outside of that, you hit a certain point where your air is clean enough that it doesn't make sense to go any higher. The only reason you would have to go higher would be a longer blade. Longer blades mean more power, right? But we're also at the point where we cannot move longer blades, nor can we manufacture blades longer, feasibly. Offshore is different. So blades for offshore are manufactured in harbors. So they get built on the water and loaded on a barge and sent out. So they don't have to worry about the infrastructure. We've bought LM, which is a company who only manufactures blades. And we bought them because they were working on a technology for multi-piece blades, which would allow us to put significantly larger blades onshore in the US. And those are essentially, it's a pinned connection. Like you have massive clevises and you pin them. The hard part, of course, is the wear and tear cyclically, right? As well as the weight in the middle of the blade, because they're entirely fiberglass. So if you put a big metal connection in the middle of it, the dynamics get really weird. So that's a challenge. Fun one, we used to try to make carbon fiber blades. Turns out carbon's conductive. So that caused a couple of issues here and there. So we don't do that anymore. But that for a while, I mean, we looked at that and we said, like, this might be the next big step for us because it is so much stronger per weight. Yeah.
Why do they almost always have 3 blades? Well, more blades would mean more torque.
That's a good question. I don't have an answer to it. I think so. The technology really originated in Sweden, I think. And the man who really pioneered this industry technology, he was doing all this research on his own. And I think that he just kind of set the bar at 3 and we never changed. But I think where it landed was there's like a ratio of cost to power there, right? And opportunities for failure. The more blades, the more opportunities for failure, the higher the cost for how much power gain, really. It also has to do, I imagine, with airflow around the blades, because if you actually you can find videos on YouTube. If you watch a wind park in a foggy or a cloudy area, you can see like the eddies that are coming off from it. And if those are too closely grouped together, your next blade might not be coming into clean flow.
Yeah, that's interesting, because if you go to the natural limit, right, then you can have enough blades, you have a circle. And so you're basically a solid, right? So I don't know what the limit is, but is there one more student question? You guys have been pretty quiet.
The other means I put you to sleep, right?
No manufacturing
I thought it
questions?
was super interesting, but I mean, I've been racking my brain the whole time. I just think it's cool.
It's a wild industry, and it's still very new. So there's still, the exciting part about it for me is that there's so much left to learn. Like, we look back at where we were 10 years ago and we're like so much wasted energy and efforts on designs that were less than fantastic. And we can only say that because of where we are now, right? And I think we'll look back in 10 years from now and say the same thing.
Okay, so I guess I do have one now.
Yeah.
So how much time and energy on these projects is spent on just building the tools needed for each one rather than like looking at the system as a whole? Because I think building the tools.
Yeah, that's a really good question. 5 years ago, it was 5 people times 40 times 52 weeks a year. That's how much time we spent on tooling. Now it's 70. I mean, 70 people, and we have like 30 openings. So obviously, as our fleet sizes grow, complexity of repairs grows, the toolkits need to get much, much bigger and more complex. As we challenge ourselves to do more work up tower, the toolkits get dramatically more intense. A lot of what we do is through hydraulic pressure, meaning movement of equipment, separating of joints. Anytime we split a gearbox, we design fixtures and we use hydraulic rams to push them apart. I worked a program with a coworker this past year where we tried to prove out that we could replace pins and planetary sections of the gearbox. So you have a planet carrier with 3 gears on it, right? And we would have bearing failures on those gears that would damage the pins. And we proved that we could pull off the helical stage, so the downwind side of the gearbox, and lower that down to the ground. And then up tower, we could pull the pins out of this assembly and replace them. And so we use a combination of an inductive heater that we designed and all the tooling that goes along with that. And then we have chiller equipment to cool the pin because everything is interference fit. And then we have strong backs and hydraulic rams to do that. And the order of magnitude it takes to pull one of those pins is about 100 tons of force. It's enough that when it pops, this 75-ton piece of equipment that's sitting on top of a pencil stick rocks. So we did it on the floor in the shop first, and it wasn't that impressive. And then we did it up tower. It was like, oh my God, we're going down. So, yeah.
All right, I think it's time to thank our speaker. Thank you. That was fascinating.
Thank you. I really appreciate you having me.
We really appreciate having you back.
Yeah, this was really fun for me. I feel like I'm so close to this all the time that I don't get an opportunity to brag about it. So thanks for letting me brag about it. And you guys have got it really great here. I remember all my professors here very fondly. You've got a great program. So really get everything out of it that you can.
Cool, topical area. Do you mind if people contact you with questions?
Not at all. Yeah, please do.
Thank you. And thank you guys for coming and staying. I know you guys have a lot on the plate. 9 more days and you're on break.
Yeah.
Well said.